Our final speaker of the morning is Dr. Sandy Liebhold. Sandy is from the USDA Forest Service, and he was over here in New Zealand anyway, visiting the B3 Consortium, Better Border Biosecurity Consortium, and working with a number of scientists on a few different projects. His expertise is in the spatial dynamics of forest insect invasions, and so he's over here to talk about that today. Thanks, Sandy.
Well, thanks a lot, Andrea. This is I'm going to go slightly a different direction to insect eradication, which is, and I have to mention before I get going that for me it's always really fun coming to New Zealand, not only because it's a really pretty place and there are wonderful people, but scientifically I always find it really stimulating, and I think this conference is another iteration of that, really, that to me that you guys, I think, in many ways are really ahead of the game, certainly ahead of the game in a lot of ways of what we're doing in North America in terms of maybe asking really good questions and tackling important problems in terms of managing biodiversity. And in fact, I have to say that the topic of this conference too is really, I think, really cool, because I think there are some really interesting intersections between biodiversity questions and biosecurity questions. And I'm going to be touching on several of those. But I think it's clear that, I'm sure here in New Zealand, and again, for me, it's one of the things I always think, for me, it's exciting to come here because there are so many more sort of horrific examples of the consequences of biological invasions, and it's really an interesting phenomenon how very often adding species actually results in a loss of biodiversity. And so again in North America, I think we probably haven't experienced as many of these kind of horrific invasions, but we're beginning to. And I can just relay one of these. This is, and I don't know how many of you are aware of this. We have a recent invasion by an insect called the emerald ash borer. It's a really pretty beetle here, and native to Asia. And it, in its native range in Asia, it's pretty much a non-problem. It just colonizes dead and dying trees. But in North America, it kills ashes, and we have 22 species of ash fraxinus in North America, and none of these species seem to exhibit any resistance to this insect. And so what we're really in the middle of now is watching an entire genus of tree being wiped out. And sort of the consequence, we're just having to really scratch the surface in terms of understanding, what really are the ecological and biodiversity consequences of this. But it's a pretty horrific thing, and so I think with these kind of things happening, we'll probably eventually be asking many of the same questions that are being asked here in New Zealand already. And so when tackling the problem of biological invasions, I always think, like many people, that you have to sort of look at the problem in terms of this sort of invasion continuum. And no doubt, there's no question that the concept of prevention is really a powerful strategy, that you can save a lot of time and money and torment by simply keeping potentially damaging species out. But in many cases, for one reason or another, those kind of attempts may not be 100% successful. And so in many situations, we witness incursions of new species, and at least one of the options that's available for dealing with incursions is eradication. And I always think it's very important to define eradication as being the deliberate elimination of a species from a given area. And here, again, here in New Zealand, I think you guys are in many ways ahead of the game in terms of both insect invasions and mammal invasions. And I know from my field, I've come over here and learned so much about some of the really impressive responses you've had to incursions over the last decade or two. And these are just some of those, which I both things like the Queensland fruit fly, but also painted apple moth and white-spotted tussock moth. And these are all examples of successful eradications. In North America, I can say that we do have the distinction of what I think is probably the first attempted eradication of an insect, of a non-native insect in the world. It was a failure, but it was kind of a crazy and ambitious goal. And the insect, the gypsy moth, which is native for most of Eurasia, was accidentally introduced by this man here, Etienne Leopold Trouvelot, who is an amateur entomologist, and he was a little bit crazy and ambitious, and he would like to play with insects. He accidentally let these insects loose, and there was from 1880 until 1900, there was very strong, the state of Massachusetts attempted to eradicate this insect, but unfortunately they failed, and I'll say a few words more about that. But that failure, I think, set the stage for something greater, and fortunately people didn't give up trying to eradicate new insect incursions. And this is actually a database that John Keane has put together of documenting insect invasions, and I think, let's see, it changes every day or maybe every month or so, and I think it's up to 768 insect eradication programs. Not all of them are successful, but the majority of them are probably successful. And so again, I think it's a change, and I'm going to say a little bit more about this, that this trend of increasing attempts and increasing success of eradication is something that can be attributed to advances in technology. And I just have to mention that many of you probably deal with mammal invasions as well, and of course there's a very parallel thing going on in the mammal world, a lot of it happening right here in New Zealand. And so I think it's really interesting to see this trend of even though the biological invasion problem is really a trying problem and troubling problem, I think we are making some progress, and I think a lot of this can be attributed to changes in technology. And I'm just going to, for the rest of my talk, I'm going to kind of talk about how these technological advances have sort of facilitated successful insect eradication. And so first off, I wanted to mention in terms of especially insect eradication, a very key aspect is surveillance. That one of the things we know that with insect invasions, they're generally not very successful unless you catch the population quite early. And so surveillance is kind of a key to the success of successful insect eradications. And with insects, one of the things that's kind of a convenient thing is that in contrast to a lot of other types of organisms, insects like to communicate with each other using chemicals. And these chemicals have been exploited for use in detecting and spatially delimiting populations for many years. And some of this actually goes back even, this is a primitive gypsy moth trap that was used back in the 1900s. You can see that there was actually a little cage there where they put female gypsy moths, and even back in the early eradication attempts, people knew that these pheromone traps were very powerful tools for detecting populations and delimiting them. And over time, there have been advances in terms of with the advance of organic chemistry and the identification of these pheromones and ultimately their synthesis and their use in pheromone traps to actually detect populations at very low population levels. And these traps have played a key role in these incursion responses, not only for the initial detection of populations, where for many types of organisms we have a network of traps that are used to detect populations, but also once populations are detected, these various types of chemical traps are used to delimit a population and also to confirm that a population has been successfully eradicated. So the next aspect of insect eradication that's sort of a key development in the sort of evolution of the technology for insect eradication is are treatments. And again, this is something that started off pretty primitively in the early days of insect eradication. Again, this is the famous gypsy moth eradication that was back in the 1880s. And as you can see, they didn't have any really very good methods for suppressing the populations once they detected them. That the methods included even just sending people up in trees to scrape egg masses off, but removal of hosts, and then even there's, in the late 1800s was the very early days of the development of insecticides. And probably the lack of good treatments is one of the reasons why this eradication attempt failed. More recently, starting really in the 1940s, there were some really important technological developments. One was the maturation of modern aviation, but the other part was the discovery of DDT. And so essentially somebody figured out that if you sprayed DDT from an airplane, you could cover a lot of ground and kill lots of insects. And so this began quite extensive use of DDT for spraying insects, and later, over time, people realized that DDT and other types of insecticides, when used over large areas in particular, can be quite damaging to the environment in many ways. And so we've seen shifts more towards we still see in eradication programs such as this is from the painted apple moth eradication up in Auckland, and the similar methods are used in other parts of the world where aerial applications of Bacillus thuringiensis, a bacterial pesticide, is used. These materials are much less, have much smaller impacts on other types of organisms, but still there are concerns about that they do have impacts on other organisms. And unfortunately, very often these eradication programs are in urban areas where people live or work, and people are not so crazy about even having Bacillus thuringiensis sprayed on them. And so there's always a search for effective but less harmful approaches to suppressing populations. And in recent years, one of the biggest developments has been the perfection of methods to suppress populations using mating disruption. This is in this case, this is a material that's used for suppressing low-density gypsy moths using the chemical pheromone is laminated between two pieces of plastic that are formed into these little chips, and they're essentially sprayed out of airplanes, and the little flakes, they stick to trees and they emit the pheromone, and the males and females aren't able to find each other for mating, and the populations in many cases will go extinct. So the next thing I want to say is about a very important part of eradication is the concept of strategies. You know, it's one thing to have these various tools, but how do you put all of this information together in a strategy that's effective for eradicating an organism? And this is actually, in fact, it's actually why I'm over here right now, is I'm part of a team led by Eki Brokerhoff at Scion, and also in this project is Mandy Barron at Landcare, and John Keene, and who's with Ag Research, and we're looking at basically developing new strategies, a little bit of crazy and ambitious ideas of coming up with new strategies for eradicating insects that don't involve the traditional approaches of blanket spraying of insecticides of one form or another. And the way we're approaching this problem is from the idea that we can learn a lot about insect eradication from conservation biologists. And I always think it's a really interesting thing that there's sort of a certain yin and yang between conservation biology and invasion biology. In both cases, we're really interested in extinction. In the case of managing or preventing, conserving species, you usually want to prevent a species to go extinct. In the case of eradicating an invading species, we really want it to go extinct. And so it turns out, I think, that we can really learn a lot from each other by, both fields we are involved with studying low-density populations and learning how to manage those. And one of the things we know, at least with insects, that one of the main causes of extinction of low-density populations is certain key aspects of their biology are not fulfilled at very low densities. And especially in the case of sexually reproducing insects, males and females have a lot of trouble finding each other at very low densities. And this is something that may be possible to exploit, as I will go into a little bit later. And population ecologists have recognized these various types of phenomena, things like mate finding failure and other types of biological interactions. And we refer to these as LE effects. It's referred to as LE effects because it's named after this guy, Warder LE, who was a professor at the University of Chicago, who many years ago suggested this idea that at very low population densities, there are certain population processes in various types of animals and plants that as populations get lower and lower, the growth rates of populations get lower and lower. So in other words, at more moderate population densities, you may have positive population growth, but at low population growth, population densities, you have population decreases. And this is a really interesting phenomenon because it creates these population thresholds below which populations will go extinct. And this is something, again, conservation biologists have recognized this with the idea that, boy, we need to keep populations above these thresholds to keep them from going extinct. In the case of eradicating insects and other organisms, we very often think about, well, how can we force populations below these thresholds so that they do go extinct? And this is a concept that several of us have thought about for a long time. And in fact, you can sort of broaden the types of methods that we use for eradicating insects and other types of organisms. There are certain strategies that we use, things like applying pesticides, where we're simply reducing the population density below these thresholds so that they go extinct. But there are some other methods that we use where we can actually move this LE threshold. So in other words, we're making it, even by moving this LE threshold, we're essentially moving the point below which populations can't persist. And there are a lot of different ways to actually move this LE threshold and to drive populations towards extinction. One of them is mating disruption, as I mentioned before, that we know that mate finding is what causes these thresholds for many insects below which populations the males and females can't find each other. And if we essentially make a bad problem even worse for insects by spreading lots of false pheromone trails out in the environment, we essentially move this LE threshold and force populations to extinction. Another approach are things what we call male annihilation, which essentially is just trapping species out, sterile insect releases, and even we know that generalist predators, very often they have inverse density-dependent predation, and so these types of interactions all contribute to these populations process such that population growth is lower at lower densities, and this can drive populations towards extinction. So in looking at this problem, one of the things in our research that's ongoing on this that we've thought about, which is really interesting, and again, we're borrowing this from the conservation biology field, that in terms of threatened species, many people have recognized that habitat loss and especially habitat fragmentation can be a really problematic thing for threatened and endangered species. And well, it turns out it's actually a pretty good approach for that can contribute to eradication. And in fact, people in many eradication projects, you'll find that people actually use the removal of host plants to eradicate herbivorous insects. And so what we've been interested in this project is, well, how does this fragmentation of the habitat interact with these allele effects, and how can we sort of capitalize this to drive species towards extinction with sort of minimal use of nasty things like pesticide sprays? And so we've been actually taking two approaches. One is sort of a modeling approach, and this has been led by Mandy Barron at Landcare Research. And we're using a spatially explicit model where we actually have, it's one of the nice things where we're actually using the Gypsy moth as a model system because we know so much about this system. We actually have information about when a male and a female, these little M's and F's, those are all males and females. We know when a male and a female are a different distance apart, what's the probability that they're going to find each other, and we can actually make predictions. Oh, okay, this female and that female, they're going to be mated, and all the other females are going to go unmated. And so we can actually make predictions on how these populations persist through time. And we also have been playing games. Well, what happens when you fragment the habitat and you have populations dispersing out into areas where there are no hosts and where males and females are going to be isolated each other and may not find each other. And just, this is a little bit of preliminary results, but it basically shows that in the more, as you fragment populations, over time, you get a higher and higher fraction of populations going extinct. And again, this is because as you fragment populations, it interacts with these allele effects, these mate-finding allele effects, and males and females have trouble finding more and more trouble finding each other. So this is one of the things we think that could be useful in guiding incursion responses. One of the things we've sort of realized is a lot of the way that fragmentation promotes extinction is very much dependent on the behavior of the different insects. And so, and there probably are, among different species of insects, there are probably some insects that are actually pretty stupid about dispersing, where they basically just totally randomly move in different directions, no matter whether there are hosts there or not, whereas there are other species that are actually pretty smart and capable of orienting towards their host plants, and the consequences of habitat fragmentation can be quite different. We're also taking an experimental approach to this work as well, and this is actually a project that Hester Williams, who's a grad student at Auckland University and working out at Landcare, and we have this really cool system. It's one of those things that for actually experimentally testing strategies for eradicating species, of course, the best method would be to actually introduce a few pest species and then play games with, what happens when you release them and do different things. It would probably be a little bit irresponsible, since some of those would probably get away. So instead, we're using a biological control agent that's a leaf beetle that's already being introduced to New Zealand for control of Tradescantia, an invasive plant. And it's a wonderful system because we can grow the Tradescantia in little pots and move them around and make host patches with different spatial configurations and essentially play these little games to see how habitat fragmentation experimentally affects the success of these eradication projects. So the last thing I was going to mention now, in terms of, again, these are all kind of what I see as kind of the major technical developments that have kind of promoted successful insect incursion response, eradication. You have to it's very important to address these issues of community engagement and social aspects. And again, I'm sure that many of you know that one of the problems is that most of these species invading of insect species, non-native insects, they unfortunately seem to always arrive in urban areas where people live and work, and so you have to be very much aware of this. And I have a really good sort of horror story of where this all went wrong, and the lack of awareness about social issues can really lead to disasters. And this was from several years ago. In 2007, there was a new incursion of the light brown apple moth discovered in the San Francisco Bay Area, and another population was discovered down here in Santa Cruz, California. This insect, it has kind of a large track record. It's already invaded New Zealand, caused some problems here. And so there was, the USDA started a big program to eradicate this insect. And actually, they took a rather progressive approach that rather than blanket spraying areas with pesticides, they attempted an eradication project using mating disruption, which, again, should have really pretty minimal impacts on other organisms, including people. But unfortunately, they made a really big mistake, which they essentially had zero public education program to sort of educate people about what was going on. There was no effort to inform the public about why this insect was really important to be eradicated, and they didn't really explain to people very well of what exactly they were spraying out of airplanes. And so as a consequence, there was this huge public uproar to the invasion. In fact, I always think it's really, if you look at some of the things that were posted on the internet, there were really creative use of Photoshop for, of having airplanes and children, and so it was a very big public outcry, and even though there was, after this public response, there was then subsequently people trying to say, oh, well, it's really not that bad, but it was essentially too late, and after about a year of this, the state government completely canceled the eradication program because it was just becoming too much of a political hot potato, and this insect now is successfully established. And I always think it's really interesting for me, it's interesting to contrast this with here in New Zealand. I think that you guys are much more aware of this, and I know with at least the painted apple moth eradication program from 10 years ago or so, which I'm probably somewhat aware of, there was a concerted effort to engage the public and to educate them as to what's going on, and so I think this is really an important aspect of all eradication efforts. And it's one of those things, I think, as biologists, we tend to sort of think, oh, well, this social stuff, it doesn't really matter. We've got a job to do. We're going to go in there and do it. But it's obviously very important. And of course, it's more than just education, but it's actually engaging the public in making them part of the decision-making process. And sort of the last slide I wanted to leave you with is this one where I really love using Google image search on Google, where you punch in a word, and it's really cool. If you search on the word eradication, it turns out that you get all these really scary drawings, and that it turns out that the word eradication is very popular for like heavy metal bands, and I think that it's an indication of what people's perception of eradication, and most people perceive it as this really scary thing. And I think that there's a real need to make progress in between communication between people in the biosecurity field, the people in conservation biology, and trying to help get the message across to the public that eradication is not necessarily a scary thing. So. That, Andrea, that's, I think, the last, that was my last slide. So. Thanks.
Well, again, we've been blessed with plenty of time for questions all morning, so we'll carry on that tradition, and I'm sure you're happy to answer any questions. And again, we'll have the roving mics kicking around.
Oh, yes.
Yeah, thank you. Sandy, good to see you back in New Zealand.
Yeah.
You're an expert on gypsy moth. Tell me, why is it that American cities such as Portland and Seattle and in Canada and Vancouver are quite happy? The residents seem quite happy to be sprayed with BTK. How did they manage to make that happen?
So I don't know if, yeah, Bill, that's actually an interesting question. So what Bill was referring to, that we had last year an incursion of the Asian strain of the gypsy moth. It's one of these things, some of you probably are aware of this, but in North America we have, in the eastern United States, the European strain of the gypsy moth, which was brought, as I mentioned, back in the 1800s. But then we have this continual stream of, there's the Asian strain of the gypsy moth, which and it's slightly different biologically than the strain we have is from Europe, and the females are incapable of flight. The Asian strain is capable of flight. And there's this continual problem of, unfortunately, because the females fly, they like to lay eggs on things like ships and steel and these other kind of things that people that are shipped in cargo to Western ports. And so there was an incident last year where it was discovered a new incursion in Seattle and just north of Portland, Oregon. And there was basically, I think there was a total of 7 locations where there were eradication treatments, all using aerial spraying of BT. And you are right that I think some of us were sort of thinking because, it's one thing is within the U.S., as many of you probably know, there's a lot of sort of geographical variation in politics. And if you were doing this in Texas or something, probably people would be cheering you in the street. But, I think in a lot of the Pacific Northwest, people tend to be a little more adverse towards aerial spraying and these kind of things. But to answer your question, the state of Washington and Oregon, they did a really impressive job of public education. They had huge numbers of public meetings. They had advertisements in the newspapers and radio spots. They did a lot of work actually on social media where they responded to inquiries and comments about it. And so I think it's actually a really good example of how, if you really are proactive in terms of engaging the public, you tend to have a lot more support than if you basically just sort of spring these things on residents, and that's really an example of what happened there.
Other questions?
I think I'm the only thing between you and lunch.
No, you're not.
Oh, the lunch isn't ready. Oh.
Any other questions from anybody for Sandy? You talked about delimitation and surveillance. One thing you didn't mention was probabilities of detection. I just wondered if you have any comment on that.
Oh, yeah, so it is a really good question, and it's one of the reasons why some insects are much more successfully eradicated than others, is that certain insects have very highly specific and powerful attractants that we can use in traps, but a lot of organisms, so like this emerald ash borer that I showed you here, as far as we know, it doesn't have a pheromone, and it seems to be attracted to host plants, but no one's figured out any kind of chemical attractant that's very powerful. So as a consequence, our ability to detect the insect is really poor. And so when it invades new areas, the only way we really usually know it is people start noticing, oh, wow, there are a lot of trees dying. And so usually when we detect these new parts of the U.S. that it's invaded, it's many years after the species became established there and widely established. So it's essentially, it's an example of an insect, at least with our current technology, it's probably impossible to eradicate. Yeah. Oh, there was one question. Yeah. Yeah, that's a really interesting question. That you're exactly right that different organisms are going to probably vary in the extent to which they have strong allele effects versus others. And so, for example, I mentioned that mate finding is very often a common cause of allele effects, and so that's one of the things if you look at actually, in fact, what insects have been successful at invading areas versus those that have not. It turns very often you'll see that asexually reproducing insects. A lot of aphids and scale insects are capable of asexual reproduction, and they tend to be really good invaders as a consequence. And they're probably also more difficult to eradicate them because you don't have this threshold arising from the mate finding. On the other hand, most species, there are other causes of allele effects. So for example, we know generalist predators will create at least a weak allele effect, and I think that can sometimes be exploited. And then there are a few other things like group feeding is sort of the famous example that's given as a cause of allele effects. That, and with insects, there are certain insects, things like bark beetles, where they have to essentially gang up on a tree as an example of group feeding. And those, again, I think can be exploited. But in general, you're exactly right. The species that have the weakest allele effects are going to be probably the most difficult to eradicate. Yeah.
Sandy, thanks for your talk and good to see you back in the country. Pheromone development, so as you recall with painted apple moth, when we got the problem, we didn't have a pheromone. And then it takes so long to try and develop an effective pheromone. And it seems to be a real gap in the system that none of us are thinking about what we actually need going forward. So are you aware internationally whether there's any efforts linked up to try and ensure that for the major forestry pest species that we've got the tools, the pheromones available to be able to trap should we get a problem? Is there a gap there, or are you aware of any work being done?
I'm just aware of a little bit. I mean, in fact, probably Max Suckling, wherever you are. There is this Pharaoh base, which I think, in fact, Pharaoh base, is that run out of your lab, Max? Where are you, Max? Is Max here? Maybe he stepped out. But there is this effort, this Pharaoh base, which is a database of pheromones, and that's the idea behind this is exactly what you're sort of alluding to, which is that there is a need to share information and to collect more information about pheromones. On the other hand, it is a really hard, difficult problem because we estimate there are between 2 and 20 million insect species in the world, and so that's a lot of insects to analyze, to characterize pheromones. On the other hand, I think we also know that there are certain species of insects that are more likely invaders than others. And then, of course, the other thing is for many insects may not use pheromones, and so we have more generalized attractants, and that's another direction things are going because, rather than having one surveillance program for one species, it's certainly probably more effective to have a surveillance program that may be effective at doing surveillance for many, many species. So there's, I think, a balance between even the sort of economy of having very specific surveillance programs versus more generalized surveillance programs that will detect many different species. So, but it is a problem. Yep.
Okay, thanks, Andy. I think we'll leave it there before you step away, though.
Sandy, just on behalf of everybody here, thank you very much for your contribution. I think it's always great to have those international perspectives and from people who understand what's going on here, I think particularly useful. Your talk also reminded me of part of the origin of this challenge was bringing together concepts of biodiversity and biosecurity, and I think you spoke to that topic very, very well. Thank you again. Good. And a small measure.